Okay, fantastic. And thank you very much for that introduction and having us here, invited to your meetup. We're very much looking forward to it. So to get started first, this is going to be a presentation regarding pretty much Kubernetes resource management, our views into that, as well as some products that we've created to kind of address some of the things that we think could really be improved in Kubernetes or in Kubernetes environments where you have mixed workloads or resource constraints. So moving on, here. So the agenda today, I'm going to provide kind of an introduction about myself and my colleague, Stefan, as well as an overview of who Unova is so you guys can get a background from where we're coming from. Then I'm going to talk about our views on scheduling and workload management, and really what we feel is really important about a scheduler in a complex cluster environment. And then we're going to talk about our product Navops Command, which is something that we've created. Our release was last November, that we feel brings a lot of our ideas to the Kubernetes space in regards to scheduling and workload management. Within the command section, we'll talk about obviously the product, also talk about our thoughts on mixed workload solutions, and show a demo of both command and some mixed workloads in action. Finally, we'll wrap it up with some Q&A. So who are we? So as I said, I'm Cameron Brunner, Chief Architect. I've been here for about 10 years at Unova, doing all sorts of different things, starting at software development and then moving up here into the more architectural role. I've worked on pretty much all of our products at this point. And specifically, the ones of note here are Grid Engine, since that will be, that's a core part of our Navops Command product. Additionally, I have Stefan Haas. He's a newer member on the Navops team, but he's been here at Unova a long time. Core developer on Unova Grid Engine and our chief designer and technical lead on our license orchestrator product, which is a license management solution for managing proprietary licensing in a kind of a high-performance compute cluster. And then who is Unova? So what we are is a software company that produces solutions for workload orchestration and container management, typically in large-scale compute environments. Our customers are generally large enterprises. You can see there's a sample there at the bottom in some of the sectors where we have some customers. Life sciences and energy are two very large segments for us. We have offices throughout the world. I'm in an engineering office here in Chicago. Stefan's actually in the engineering office there in Regensburg, Germany. And we also were the home of Grid Engine. So if you've ever heard throughout your career the term Grid Engine, maybe working with an HPC in an HPC context, we're pretty much producing, we are the official home for that product, producing a commercial version. We also have released some open source versions. At this point, we employ a lot of the folks who wrote the open source versions over the last several years. That's where Stefan came from. As well as taking kind of a transfer of ownership from Oracle after they had bought Sun and acquired Grid Engine. So now on to scheduling and workload management. And really, from our background in the HPC space, we've managed, thousands of applications on, hundreds of customers over about 20 years. That's how long our team's been working in this space. We've learned a lot of things about scheduling and workload placement and what's kind of consistently important across all of these environments. So one thing that obviously becomes very apparent is we live in a world where resources are finite. Obviously, that's easy to see if you walk to your lab and you see, you have 5 machines and you can fill them up. But this extends really to any type of platform. I mean, typically you'll have, budgets placed on you when using cloud resources. You could have quotas placed on you as well, which enforce a limit or a resource constraint on the entity being limited by the quota. So it's not infinite. We need to consider that when scheduling work. The other tenet, of course, is that people really want to get as much done as possible with resources that they have. So, if they're investing in local hardware, or if they have their quota, they want to make sure that they can be as productive as possible. So this, of course, means you need to meet application SLAs. If you're running in your cluster something that needs to be up all the time, that needs to continue to be up. But you also need to be able to use your resources to make sure you can move that product forward, do effective testing of that product, and be able to get information about your processes in terms of improving improving the process, you're improving efficiency, to be able to get more work done, be able to get your products released faster, and provide better uptime. So our general solution to these problems, and what we've learned here, is to pretty much unify resources into large compute clusters. Generally, eliminating silos, combining things into as large as manageable cluster as really can be supported in the environment, followed by the addition of a very feature-rich scheduler, which can then manage the placement of work to meet the needs of the business. This allows, even groups with lots of different budgets to pool resources together and make sure that each group gets what they've contributed while still being able to meet the needs of the business. So you may ask, what's required of a scheduler that needs to be pretty much the manager of all the workload across several groups or heterogeneous workloads and multiple teams and groups? And we really believe these three points here are pretty much the most important ones. So specifically, prioritization is important. As I described earlier, you can run into resource constraints. You'll run into it, with budgets or the quotas. Well, with prioritization, you can then determine, not only which which job gets to run next when you have run up against one of those limits. You also allow higher or more important workloads to get access to resources that are more favorable. Often a workload could run on something less, but it would run better if it had, some more RAM or some more CPU available. This will allow you to have your more important resources get what they need, and then allow the less important resources to get placed on, minimal or whatever is remaining. Also, more information for the scheduler, the more information that's useful that the scheduler has, the better. Obviously knowing more about the resources that are available in the environment, knowing what type of work wants to run, when it wants to run, when does it need to complete. Really, all in the end, as you keep adding these points, you can create more feature-rich policy that more specifically target the business needs and allow you to make better decisions on what work to run when hitting one of the resource constraints that I was describing earlier. Finally, you need to have a method to generate information regarding the scheduling decisions, and then be able to analyze the scheduling decisions to make sure that your policies are being met and that the business needs are being met. This can allow you to additionally manage for future capacity growth. If you need in 6 months to be able to double your compute capacity, having this type of information would let you know what resources you need to buy in order to improve your throughput by 2. It may not be buying twice as many machines, for example. It also allows you to identify bottlenecks, and this will be where if you have quotas or machine constraints that don't really match the workloads that you're coming in. Like, let's say you only have 10% GPU machines, but 90% of your jobs are wanting GPUs. You'll be able to detect that and see, wow, I need to buy some more machines with GPUs in order to get better throughput and time to market on my product development. So this brings us to our product, Navops Command, which really, it takes what we've learned in the HPC space, where we've applied all those principles that I've just described, and it brings it to command. It brings it to Kubernetes. So it allows you to run, take kind of the unprioritized workloads that are currently present in Kubernetes, prioritize them, match them against all sorts of additional policy attachable objects, such that you can get tighter placement and be able to really share a cluster that's running very many different types of workloads across many different types of groups and users, while still maintaining a very high utilization rate of your cluster. So what is really Navops Command? It's a multi-container application. We designed it as very container-friendly forward. So everything's done pretty much in a container. And it's actually self-hosted inside of Kubernetes. So the 3 containers that exist inside of the main Navops Command pod are one for managing the scheduling decisions, one for bridging the data model between Kubernetes and our internal scheduler, and then one for storing our internal configuration. We additionally have a container that runs our UI, our web user interface. And that runs as a separate pod, allowing an admin user to be able to configure the policy and the scheduler dynamically. The end users interact with Command just as they normally would, and this is because Command implements the third-party scheduler interface provided by Kubernetes. So really, what we do is we just plug in and we take, using the third-party scheduler annotation, we take pods that are either targeted directly for a command when command is running as a non-default scheduler, or we would take even the default pods, so pods without a annotation if you configure command to run as your default scheduler. Additionally, properties can be added to Kubernetes pods to leverage more of the features inside a command. But this is all done through standard labels and annotations inside of Kubernetes. So really, as I said, in the end users, they don't need to know anything about command in order to use it, but they may add additional attributes and annotations in order to leverage certain policy inside of command. So the key value here is the scheduling application that we have inside of command is actually a containerized version of our core HPC scheduler. So you get all of the functionality and features that are baked into that. So here is a kind of graphical view of what I was just describing. So you can see right there kind of the communication channels between the Navops Command pod, the Kubernetes API server, and then the actors in our environment. So as you can see, the admin is primarily the one who interacts with the system to configure the policy, and that can be done through the web UI or our Navops CTL command line utility. And then the end user uses kube control like always. The line right down there at the bottom is of note, is that's how we actually tell Kubernetes through the binding of a pod to a node to actually schedule the pod. That's the other component of the third-party scheduler interface for Kubernetes. And additionally, the Kubernetes objects there between the Kubernetes API server and the backend, those are streamed using the standard Kubernetes watch functionality. So now on to the next slide. So we have provided here with command, this was the release that we did in November, where you have now this ability to add a complex policy to your Kubernetes scheduling decisions. And that's great. You get our 15 years of experience doing that and a lot of great features. But we found that some of our customers want to run in a mixed workload environment. And what that means is really they have some containerized applications that run inside of Kubernetes just fine, but they also have a lot of workloads that don't necessarily run under Kubernetes. And they want to run those just as they have before without really modifying anything. So what we've done is actually fully containerized Unova Grid Engine and made it to, allowed it to run under Kubernetes to provide pretty much an HPC cluster that's hosted by Kubernetes. Now, when running under command like this, you additionally have command placing the Unova Grid Engine components, Unova Grid Engine pods, which then will schedule the actual HPC work, inside of them. So this allows you to run both Grid Engine in a dynamic scaling environment on top of Kubernetes and be able to run your legacy unmodified HPC applications. With that being said, I'd like to turn the presentation over to my colleague Stefan, where he will describe the demo environment and then go through a demo of this functionality.
Hi, welcome also from my side. So this is the demo environment I set up for this little demonstration. So let's imagine a company with two different teams. We have CI/CD, so continuous integration and continuous development on the one hand, and some ops team, which is also divided in a batch and a services team. We have a couple of pods and workloads running later on in the demonstration. The CI/CD team will have some work for development and some testing work. The batch team has the grid engine, the Unova Grid Engine running inside, and some back and job replication controller. And we have the services tasks on the other hand, which does administration and production stuff. This is running on, so as Cameron said, this is running on Kubernetes, which has Navops Command on top of it. And my demonstration is a simple Minikube VM. So I need to share my screen now.
Here, I'll stop sharing mine.
Yeah, exactly. Okay, can you see my screen?
Yes.
Yes. Great. As we heard already from Cameron, Navops Command provides a virtual multi-tenancy on top of Kubernetes. It allows to share one cluster among multiple teams, as I said, applications and services. And it even allows to run containerized and non-containerized workload in the same environment by running Unova Grid Engine as the workload processing service for these non-containerized applications on top of Kubernetes. And this is what I'm going to demonstrate now. Let's dive directly into what Navops Command mixed workload support allows you to have running simultaneously. So you see here kube control, get pods command running, and you see here we have running currently a UG Master service instance, and we have running 2 UG execution daemon instances. And I will start right now a couple of backend jobs and front-end job controllers. You will see what everything is about that. I will say later. This is the view of the Grid Engine job. So within Grid Engine, we have a couple of legacy jobs running, which are called in sys view, Galaxy, and GS. So there are 3 jobs running on the D3 and D4. And we have 3 jobs running here on this execution team, is this V8KLX. So we have, this is the Navops Command and Web UI. On the left side, you see here the policies you can manage via the policy management. I will show you how to change things like the proportional shares. What you see here is an organizational breakdown of how the entire cluster resources are to be used. It's reflected in the proportional share policy of Navops Commands. The full width of the diagram represents 100% of the cluster resources. And at the highest level, I have split these into between CI/CD and the ops. These are the teams I have shown you in the slide. Below CI/CD, we have the projects for development and test. For simplicity reasons, I will not run any pods within those projects. Otherwise, it would get too much input, output of the commands you will see. On the right side, we have the services team and the batch team. The batch team is also divided in Grid Engine and backend, and as you can see here is some kind of 80-20 between backend and Grid Engine. Let me click on that, then you see that. This means that 80% of the resources which are available for the batch team will go to the backend project, and 20% of that will go to the Grid Engine project. For that, to see that a bit more easy, I used an additional feature of Navops Command, the so-called runtime quotas. This means those 2 projects are limited to run only 10 pods at a time. So we should see later that there are running 8 job backend replication, 8 job backend job controllers for the project backend, and there should run 2 Grid Engine execution daemon hosts. This is configured, as I said here, in the runtime quotas. Navops Command automatically creates for each namespace you have in your Kubernetes cluster an entry here for that. So let me click on the configure quotas. I configured already a limit for that, and I said that the projects, Grid Engine and backend are limited to run 10 pods at a time. This slide here means that both of them combined are only allowed to use to run 10 pods. If you would disable that, it would mean that backend is allowed to run 10 pods at a time and Grid Engine is allowed to run 10 pods at a time. Let's switch back. So you can see here we have running 2 execution daemon pods, as I said, and 1, 2, 3, 4, 5, 6, 7, 8 of the backend jobs. This is exactly what we have seen in our proportional share user interface of Navops Command. So let's go back to the proportional share screen and change that. For example, 80-20 for grid engine and 20 for backend. Save that. So this will take a while. Let me see. Till that we will see the changes. So now you can see we got another UG execution daemon part pending. Let me make that view a bit better. To only see the running parts. So now you see that Navops Command scheduled a couple of another execution daemons and stopped a couple not more backend jobs. And in a couple of seconds, we will see here on this screen that those new execution daemon pods will automatically get added to our Unova grid engine system. And if there are pending jobs which are waiting for resources, they will get automatically used by the grid engine system. So a third one got already added to the cluster, the K5Q. So this may take another couple of seconds. So here, now we got another one. So this so now what have you seen the last couple of seconds? So you saw a single Kubernetes cluster that ran standard containerized workloads along with Unova Grid Engine as a workload processing service for this non-containerized workload on top of it. So I think I was pretty fast, but this was pretty much what I wanted to show you. Cameron, do you want to show something additional?
If you could go quickly over some of the the configuration objects, that would be fantastic.
Sure. As you can see here in the proportional share view here, there are a couple of projects configured like dev, test, grid engine, backend, and whatever. Those you can configure here on the left side. So for example, let's have a look at the grid engine project. You can add here another, these projects, and you can give to users or to groups access to that project. Or you even can, for example, restrict that some groups are using the resources of that project. What else? You can also add access restrictions to your namespaces in Kubernetes. For example, in this example, in my mixed workload namespaces, the projects backend, grid engine, and production are allowed to submit their workload into this namespace. Again, you can deny something you can deny accessing that mixed workload namespace. You are also able to limit the hosts to which the Kubernetes workload should go to. In my example, the Navops Command scheduler internally will use all available hosts.
So I think at this point, we can turn it over to QA while he has it open right here. If there's anything anybody would like to see or has any questions, I'd like to be able to jump into any of the screens as part of answering them. So.
Perfect. So first of all, thank you so much for that presentation and demo. So if you're already familiar with this, the way that we do the Q&A is you send me a private message on the group chat, and I will read it out loud in order. So if you click on the chat feature at the bottom of your screen, you can select my name, which is Online Meetup. You can send me any questions you have, and I'll read them out loud. Sorry, I muted myself while I was reading a question. I'm sorry. So our first question is, how do pods get associated to project through label?
Okay, so Stefan, could you open up one of the YAML files for one of your controllers? So I brought this up a little bit when I was doing my presentation, and it's through, there's a couple of different ways. So the way that we're using this in the demo, you can see there in the labels section, about the 10th line down, it says navops.io/project. So that's a special label that Navops Command is actually looking for. So that allows this specific pod to be bound to that project. We also support, and we didn't necessarily show it in the UI, but I think Stefan can pull it up right here. We have a thing called application profiles down in the configure section. Oh, we don't have any in there right now. So yeah, perfect. So we also have application profiles, which allows you to add a whole bunch of, let's say, labels or annotations that you could add manually or individually to a pod. Allows you to group them under this one kind of consistent application environment description, which can then be attached to the pod instead. So for example, you see on here down at the bottom, there's a project item. We could create a new application profile, add the project backend here, and then reference this application profile in the YAML file as well as a way to get the project.
All right, great. Our second question is, does this support federated Kubernetes clusters?
So federation is a very interesting concept for us. Right now, in general, we haven't really been approaching the federation style of growing an environment. So right now, we would generally look for a single cluster as opposed to a federated cluster. If there's some, we could take some offline discussion with the people who are really interested in federation, but it's something that we discuss quite a bit internally. But I guess to directly answer the question right now, this is not targeting federated clusters.
Okay. Our third question is, what does command give you that the stock Kubernetes scheduler does not?
So the most important one, I believe, is the prioritization of workloads and managing situations where you have resource constraints for the entities inside of your group. So that's really why I brought that up quite a bit during the presentation. So specifically with the Kubernetes scheduler, they have quotas, but the quotas are done at admission time. And what that means is they don't prevent pods from getting in the system. So the scheduler doesn't really know how much work wants to get run when quotas are being hit. Whatever pod happens to get in when the quota actually goes from being in violation or being hit, whichever one tries next is the one that gets in. And that's likely going to be from some controller that you have running in the system. So that really makes it difficult to be able to consistently or predictably manage which workloads are going to run next when you're running into any type of quota or limit. So really where command will let you operate is in the case where you will have lots of quotas. You'll want to make sure that the important work runs properly in those environments. Our quotas, like I said, they're runtime quotas. So what you would see, and maybe you picked up in the demo, is there would be pods that would be pending and sitting around pending, waiting to run. And that's because our scheduler won't schedule them because they're violating the runtime quota. So those are two things right there. And we believe those two are very important in order to achieve multi-tenancy when wanting to share the resources efficiently across your teams and groups.
Okay. Our next question is, does changing the resource limits via the slider kill all pods for this namespace, or just the ones which will breach the limits?
So right now, the workloads that we were running in there actually were run to completion workloads. So they were terminating, and it's once the capacity was available, the higher priority jobs after the slider change took over. So we are working on in the next version of the system to be able to do preemption and eviction of workloads based on violations of the policy. But that wasn't shown in this demo.
The presentation mentioned performance bottleneck identification. Mm-hmm. Would you be able to show how that's done?
So that is in the product that we have currently under development as an addition to the Navops suite called Navops Control. We have it as part of our core grid engine project. So the way that I would describe this is we would know our scheduler keeps track of all of the requests for work that are made, and it will record this into a reporting and accounting file. Through that file, we can see, what's being requested and what's being run and determine why things weren't being able to run. So we'd be able to see that, you weren't getting efficiency out of certain job types. So what we'd be able to do and what we have in our Uniside product is, graphs and reports for showing that type of thing. So that will be integrated in a visual environment in the Navops product suite. Right now, it's not very interesting because it's just, you would have text files that show what's being requested and what's being run. We still have to parse those and generate the graphs.
Cool. Next one's kind of a compatibility question.
Mm-hmm.
Can using this with multiple other schedulers cause issues or cause the restrictions to be broken? Right.
So right now the quotas are based on, so they're initialized. So capacity of resources is initialized based on what's being provided by the kubelets on all of the machines. So we get that through the API server. So we do properly initialize things like memory and CPU capacity. What we do not necessarily detect the current consumption from other schedulers at this point. This is something that we have as part of our pretty much next release of Command, where we'll be adding more resource collection to be able to detect the consumption of the resources that we care about. So the answer to the question right now is no, the Command is not aware of consumption of resources by other schedulers, but that is on our near-term roadmap.
So I guess this might be related. Will this work if I'm running HA Kubernetes Masters?
Yes, there's no reason why this wouldn't work with HA Kubernetes Masters. The only interface that Command has with Kubernetes is via the API server, which we discover using the standard Kubernetes Go client libraries. So as long as that is failing over properly, if you have an HA failover with your HA masters, it should be fine. Because literally what we're using is the standard Kubernetes client to do gets and watches of the Kubernetes APIs and API models, as well as then running kind of the stock Kubernetes binding command to bind a pod to a node. But both are fundamentally driven through the core Kubernetes Go client libraries.
Perfect. That seems to be all the questions we have. I'll just wait a second to see if any more come in. Yep, seems that's not the case. Wonderful presentation and demo. Oh, here we go. Just the last question here. Can it be used to rebalance pods?
So could we get a little bit more detail in rebalancing? Is that like to spread, like when it comes to like pack or spread placement of pods on nodes? Is that the question?
Taking nodes out of the cluster.
Oh yeah, so yes, definitely. So what would happen is the way that would actually happen is when you like cordon a node, for example, it would trigger a Kubernetes actually manages that. So what would happen is you would cordon the node, and those pods would get removed as as appropriate based on Kubernetes changing the deleting the actual pods, and then Command would see that the pods were deleted and release those resources. And then, as they get thrown back on, as the controllers try to recreate the deleted pods, Command would see those and place them based on the current state of the cluster and the current policy configured. So, they would get put on different machines, and they would get put on different machines based on, their priority, their currently calculated priority, as well as the resources available in the cluster.
Great, perfect. So now we do not have any more questions, and wonderful presentation. wonderful demo, and we had a great Q&A session. Those are always good. Thank you so much for coming. You can reach them on Twitter at NABUPS. And do you have a contact page on your slides?
I don't have. Well, here, let me see. What do I have?
Okay.
Just go to our website. Everything's on there. So here, let me. Could you stop sharing your screen, Stefan?
Yeah, I think you already did. Yep.
Okay, good. Let me get back and I'll show it. There. So yeah, and thank you very much, and thank you all for the great questions. I always love answering questions, so it's always good to hear good ones. So thank you very much.
Perfect. Thank you so much. I'm going to leave the group chat open just in case you guys have any questions amongst yourselves that you want to discuss. But you're welcome to leave or stick around and discuss. And thank you so much for coming. We will be announcing the next online meetup shortly, so look out for that. And have a great end of the week. Thank you, everyone, for coming.